Hi, my name is Matt Austin from RC Products, and in this video we are going to start looking at damping. I call this one part one oils. I'll try and make this quick. Previous take I was gas bagging for over an hour, so I will move through this quickly. There are a lot to get through, but I'm just looking at how oil affects our dampers. So what I will do is go through a quick overview. We'll look at the damping curves and flow types and how does the oil affect our damping. This has been, I've done a lot of testing to do this. It is very new. I've searched the internet, the web, and there's not a lot in terms of real dyno tests of our RC shocks, and our shocks are different to how the bigger shocks work and how they did work. A lot of other different factors that came into play that make ours a little bit specialized. So hopefully you find this informative. And here we go. Right, so dampers, they convert a kinetic energy into heat. So it resists the movement, it resists the kinetic energy, and it turns it to heat, and therefore it slows down that force. So in our vehicles, you need the damper there to help reduce the oscillation of springs as well as control body movement. And depending on how you set up the dampers is how they'll operate within the car. But they are critical for a car's handling. And yeah, unsprung. So unsprung is anything that's sort of hanging off as I pick the car up, and then the sprung weight is all these components that are above the spring itself. All right, and damping is a product of both the piston type and the oil viscosity. In our case, the oil viscosity. So it is very important that you can't just sort of look at one in isolation. You do need to look at the oil, and we'll go through some of that in a second, but they are equal parts in the damping equation. You can't have one without the other. Okay, so damping curves, basic damping curves, linear, a 1-for-1, 50-50, 100-100, 200-200. So it's just a 1-for-1 linear curve. A lot of your normal road vehicles are sort of these sort of curves. A progressive curve is a 1 to more, a bigger return. So in this case, at 100, you might be, instead of 100, you're now 120, 130. At 200, you'll be at, say, 270. So it's a ramp up in force. As the velocity gets higher, you get a more return in force. The exact opposite is a digressive curve, where as the velocity ramps up, you'll get a less return in force. So, and then an orifice type of piston. Back in the sort of vehicles prior to the 80s, or anything that had just the orifice type, not a shim stack or anything more advanced than that, you would get into this sort of, depending on the the conditions, but it would be typically called a turbulent or quadratic type of curve, where every time the velocity, once it is in that turbulent state, every time the velocity doubles, you get a four times force return. So at say at 40, and you've got 40 here, at 80 you'll be at 160, and at 160 you'll be at 160, 320, 640. So it's a massive ramp up in force, and that was the main contributor to what caused those vehicles back then to have that pack, where you would race along the freeway and your vehicle weighs 2 tons, your hydraulic damper hits something like a pothole, you've got a lot of moving unsprung mass there of cast iron, drum brakes and steel wheels. It's heading up into the chassis, and the hydraulic damper, with all, it couldn't quite absorb all that kinetic energy, and the kinetic energy then gets transferred into the vehicle itself, and it lifts the vehicle in a sense. Won't go through all those specifics on pack, but that's how that sort of came about, and where shim stacks and other clever ways of doing suspension got rid of that type of behaviour in those type of cars. RC shocks, where do we sit? We'll soon find out. Okay, shock dyno. The one I've got measures 2,000 times per second, or 0.0005. So half of 1,000th of a second. It will give me a data reading, and a 10-second run, I'll get 20,000 rows of data. So massive amounts of data. Without a dyno, you're guessing. All right, I did 2 tests, 21 mil stroke, one at max velocity at 130 millimeters per second. So that's what we would help me with my low speed. And then one at 900 millimeters a second, which is obviously a lot faster, about 7 times faster. And that gives me my high speed type of reading. I didn't go through all other velocities. I wanted to keep this simple. I think the message will still get across. So a load speed damping could be anything under 100 millimeters per second. Penske shocks will say, I think it's under 3 inches per second, which I think is about 200 mil. I could be wrong, but it's a slower type of movement. It's your chassis sort of movements, roll, anything where the dampers are sort of operating smoothly. And then high speed is everything above 100 millimeters per second. And that would be your jumps and your high speed bumps, anything where it's really sort of rocking and rolling. So for us, we're probably spending more time in that high speed perhaps. But I'm not setting these ones in stone, but they're thereabouts for this particular presentation. Okay, to give you an idea of what 130 millimeters per second looks like. So that's fairly slow, and that's at the higher end. I couldn't go lower because other things start mucking up the test results, say the seals, the O-rings themselves start imparting a bit too much of a force. So I'd rather not. Okay, 900. And that's quick. You can keep up with that. And just I didn't use this one. That's what 1.9 looks like, and we're flying. All right. This is what the results give me. So in the 130 per second, we're sitting about 800 grams of force, which is not a lot, but when you think the corner could be 800 grams, you're still coming close to actually lifting. But that's about typical. 900, and this is still the 130. I've just overlaid the 900, and you can see there it's a fairly smooth sort of climb as it winds up to speed and then gets up to that maximum velocity. And then we're sitting now at close to 10 kilos. These are in newtons. You just divide it by 10 to get kilos. And you can see there it's a nice smooth line. I do prefer these reports to the other type of reports you can get. This just gives me a nice sort of look at how it behaves in the long term and how it winds down. I like it. I can read it. And at 1.6, you can see here it's tracking nicely with the 900. It's starting to speed up. Here it says goodbye to 900. And keeps going. It's still a reasonably smooth path. And I say that a smooth path, it's not doing any big jump hockey stick type increases, which would suggest a turbulent curve. It is still quite smoothish. Here it's starting to get messy, and this is the reason I didn't use a 1600 millimeter per second test, because it just gets a little bit too sketchy here. 900 will give you a good idea, and it's still quick, as you can see by the video. All right, so if I then added those two in a graph, this is what the actual looks like. If I then took the low speed and just extrapolated that number in a linear sense, this is where we sit. and we'll go in more detail of what those look like. But you can see here, it's a big difference. We're 10 on 20, 20 on 10. But if I put a quadratic type of equation into at some point in that line, it ramps up a lot quicker. And again, you double the velocity, you get a 4 times return, and that's explained in Paul Theed's book, the Suspension Bible. Caused me a lot of headaches. Some really good stuff, but the part on quadratic damping caused me a lot of headache because it is the Bible, and he does talk about that quadratic damping for orifice pistons, and I was pulling my hair out for quite some time because I just couldn't get that result. No matter what I did, I couldn't get that result, and I'm thinking I'm doing something wrong, and there are reasons, and we'll get to that. And that's why we can't use. There's some great stuff in that, and I recommend to read. You could probably get about that much of the book and throw the rest away, maybe that much. A lot of it's probably stuff you don't need, but those few pages are gold, for me anyway. Quadratic turbulent, if I started right from the get-go, it ramps up exceptionally quick. And that's 75 kilos at 1.1, 75, 150, 300 if it gets to 2.2, 300 kilos. We're not getting 300 kilos on that. I think the most I've got these up to is about 300 PSI, or so 40 kilos, and that translates into PSI of 300. The fluid will keep flowing. There's nothing stopping that fluid, but just the mass of the vehicle just will not, the shock just lifts it straight off the ground. It'll actually throw it in the air at 300 PSI, or at say 600 kilos, 300 kilos. Why is it all happening this way? Well, it's in a theoretical sense, you can use a Reynolds number. A Reynolds number, you plug in these velocity, the pipe lengths. In our case, it's the piston depth. Still applies, even though it's a short length, because there is a length to diameter type ratio, and that can determine the flow regime that you would apply. All gets very complicated, not going through it all, but we're going to look at the viscosity of the oil and potentially how these things impact our damping. Laminar flow, once you plug all these things, it'll spit out a number. If you're under 2000, it would consider that flow a laminar flow, smooth, where the viscous damping is greater than the kinetic input. So the inputs, my kinetic input, the fluid is saying, yep, I can absorb that easily without getting messy, and it all keeps it all nice and smooth. And the how it's converting that kinetic energy is through a sort of a more shear rubbing up against each other and friction that way, and that's how it creates its resistance. It's that resistance. The viscosity is that resistance to movement. A turbulent flow is greater than 4000. It is a chaotic flow. It's where the kinetic inputs are greater than what the fluid can sort of handle in a calm sense. It gets a bit messy, and other things then start to come into play, which is your inertial effects. You've got drag, a lot of other factors come into play. So shear is still there, but it is not the prevalent type of form of friction. The inefficient flow is what really sort of starts impacting on your on that force. And again, that's why you get that massive ramp up in terms of the turbulent flow. All right, so for those who look at those two numbers, you go, well, hang on a second, you got 2000 here and you got 4000 there. What's in between? Good question. All right, so going from laminar to turbulent is just not a flick of a switch. It's not instant. It needs time to transition. Now, transition is a Reynolds number of 2K to 4K. It doesn't mean it is eventually. Now, that if you do get a flow type which calculated at say 3K, it doesn't mean it's going to get the turbulent at above 4. It can stay in that sort of in that number, in that sort of flow type, and that's perfectly okay. So there are essentially 3 flow types: your sort of smooth, laminar, your transition, and your turbulent. Turbulent, messy. So designated driver, 12 beers, now hitting the spirits, anybody's guess. Right, where we get the good stuff, the meat on the bone. All right. Thank you, Justin Moore, Coast to Coast, for giving me this JTP oil. I did give him a system in return. That he wanted me to test some pistons, and I said to give you a really more accurate result, I need the oils that you use. He sells JTP, and he obviously uses JTP, so he gave me a lot to sort of test, and that was good. So thanks again. And flat pistons and these inserts. Right, so we tested both at a low speed, 130 mils per second, and a high speed at 900, and I got the test results off the dyno. Where I got this low speed result, I then gave a theoretical extrapolated sort of linear curve at 900, and by doing that I could then get what the variance is from a linear curve, theoretical linear, to what the actual result is. So that's 900 actual versus a linear curve theoretical, and then I can then plot the variance. So 300 CST oil in this particular case. I'm not going through all of them because I just talk too long. So this one here is 69%. So we're 69% more sort of messy than linear. And down here we've got the red, big red, 40%. Very, very, that's good. I've got averages. So the average is 10.4 kilos at 900. Average on a linear curve is 6.9. So overall 50%. So it's quite a progressive curve. But 400, 33% increase in viscosity, 400 over 300, 33%. At the low speed, we get roughly the same, 30%. High speed, however, we don't get that same ramp up. So even though we've increased our viscosity 33%, we only get a 12% increase. So our net return is a lot less. 500 now, 25% increase. 18% increase in the 500. Still okay. I'm happy with that. There can be other factors at play here, but here we don't get the same return. So we're getting a reduction in return again at the high speed. And here you see here we've gone from 50, 29. So we've halved our sort of progressive curve and we're heading towards linear. And here we've virtually halved it yet again. So we're now even more towards that linear curve. 600, 20% increase. So you can see here they're slightly going down because they're obviously 100 on 500 as opposed to 100 on 300. It's a different percentage. 20%, 18%, so fairly close, but only 9%. So there's a slight difference here. I'm not getting into CSTs of the JTP oils. You will get slight variances, but that's not what we're looking at. Not interested in testing CSTs. So 12.3, we've got a slight increase. And you can see here, we're not getting massive increases in high-speed damping on these oils. We'll get into why later. And here you can see, again, it's a slower, so the theoretical linear is starting to close in yet again, a big leap forward. 700, we're now essentially a linear type of curve on our compared to our theoretical. So we're 2%, so we've got 17 and 16, so we're back on linear track. This one was an anomaly. Linear track here, 2.1, 6% return. So our net return on on our higher CSTs in the high velocity type of area, it's not as good. And on a linear theoretical curve, we're now under it. So you could say we're digressive. I'll call it linear. 800, 2.2. So we're starting to slow down in terms of our increases. So we increased 14%. We're only getting a 7% increase, but 5% in the high speed. So, and now we're even more digressive. And that's the big call out that really hasn't been done in any sort of depth that I'm aware of. And if anyone has seen something previously done for RC shocks with silicon oil, shoot them to me at these velocities. I've seen some with velocities that don't really, they're not high enough, and they're not done in a way that I would rely on. But this shows two distinct findings for me. All right, so the detail behind these ones I'll have on the on my website. I'm not going through them all here; it'll just take too long. But you can find them on the website. Here, the 800 I'll show, but you can see here the 5 by 1.5, 6%. So this one at no point got into this type of linear to digressive type of curve. It stayed. It's sort of like the odd cat out of the lot if you take out these magical inserts, these little things. But it's the odd one. It has a different type of property to the other ones I've tested. Now, when I do get to the piston type testing video, maybe I'll add a few more to it. But for the moment, this one's the odd one. And here, even though we've got 800, it still stays progressive, which is interesting. And I've tested this one and this one. I've done hundreds of tests with these pistons, and this one really just this is not just a once-off anomaly. This is consistent. Okay, so key findings: lower viscosity oil is more progressive than higher viscosity oil. So the bigger the number, the more progressive to the linear. So if you want a progressive type of curve, you would look at a lighter type of fluid. Low speed damping aligns closely with the oil viscosity, and which aligns to the theory of a laminar shear type of flow. So when they determine an oil viscosity in a CST, center Stokes, they basically put it in a cup and they let it flow under gravity, and they time how long it takes to empty the cup, or where it becomes not a smooth flow. So there's a lot more to it, but essentially it's its resistance to moving, and it's a shear resistance. So it sort of falls in line with that type of theory. So the shearing of the fluid at high speed, the shearing of the fluid is still there, but there are other things at play. As I said before, you've got drag, you've got inertia, so you actually got the fluid itself and the mass times velocity squared. You've got actual momentum and the ability that fluid and its resistance to move. And as it gets faster, it's just going to resist that movement, especially if it starts getting into a transition, not turbulent, but in that transition, it is still creating a very inefficient flow, and it's causing its own influences on that force. So it's not necessarily the shearing, and this is why you don't necessarily get a linear type of response between 130 and 900. You're not getting increasing the viscosity of the oil, doesn't necessarily get linear on both curves. It's there are different factors at play at the low speed, shearing, and at high speed, you've got your drag, inertial effects, as well as shear. And there might be a lot more that I've missed, but it is different. So those who are relying on spreadsheets of 2 columns where it's just a number of holes and perimeters and areas and what have you, that's not how the damping will work. It's If there's a correlation, I can't see it. Someone else can get my table and see if they can make a correlation. Good. If you can make one that works, I'll get you a set of these. But I can't quite see it, and you'll have to look at this 5 by 1.5, and you can see there's a bit of an anomaly there. Okay, so what would it mean for a tuning option? Linear piston oil combinations may be better for bumpy tracks, which is controversial when this has always been considered the champion of bumpy tracks. But I would argue with this data that the 8 by 1.3 is just as capable. It's got a low speed, it's got the same type of low speed characteristic, but it won't load up under any of those oils more than the 5 by 1.5. So this is more linear. So if it hits a high speed bump, it's not gonna pack unless you want it to pack. That's a smoother. The 8 by 1.3 is a smoother type of piston than the 5 by 1.5. And then on a progressive piston oil combination might be better for a smooth track with large jumps, which is again opposite. The only challenge with, say, a 5 by 1.5 is you may not get that initial amount of pack or damping. I shouldn't use pack, damping. And obviously position sensitive can do both. So if I wanted something firmish in the middle, I could run my blue in the ride zone, and if I wanted to sort of taper off a bit because of bumps, I could put a purple, and I would get then, say, a nice firm low speed ride, and I can then, once it hits the bumps, I can, rather than going there, I could go here and get a bit of a pressure relief. And while I'm at it, there is in play a yellow and a white to be added to this list, which I'll do in due course and I'll put on the website. But there's a few more tuning options in the pipe as we speak. Now, just to reiterate with what I was discussing with the damping and how higher speed damping is influenced less by viscosity and more by other factors, that applies where we've got a progressive curve at high speed. I just want to make that clear. Where we are at a higher numbers above what we call our linear curve, there are other factors at play other than those shear type forces, laminar flow. And when those other factors come into play, they have a greater impact. So a quadratic damping curve, for example, will be more forceful in its resistance to kinetic energy than a viscosity will. Viscosity or a laminar flow will be nice and smooth. It's orderly. It's not as resistive. So I don't know. It could be like, for those who've got kids or those who've witnessed this, it's like having a 5-year-old child in a toy store, and your 5-year-old child sees a toy and wants, and I want to get that toy. No, you can't. A laminar 5-year-old child will just hold you by the hand. You can walk out nicely. A transition turbulent type of 5-year-old child that wants that toy and then completely goes bananas, that same 5-year-old child is going to be a lot harder to try and drag out of that store. So I'm not sure if that analogy works, but it's just got more sort of bang for its buck, and that's why you won't get a linear increase as you move down this column here. The percentages are smaller relative to the increases in viscosity. These are transition flows, with a higher Reynolds number, say, in the theoretical sense as we went through before. And as we're coming into here, as we're getting into that thicker viscosities, it is now starting to play a more dominant role in that damping. And it is sort of replacing it. It is calming down that flow type. So effectively, the Reynolds number is starting to come down, and that's why you're seeing a sort of exactly the opposite. Instead of going from linear to transition, in this sense, we're going from transition back towards a more laminar flow as the Reynolds number starts dropping, because as you're increasing our viscosity. So I hope that makes that clear. And that, again, that's why you won't see these huge numbers, because there's a sort of a converting of the type of flow resistances. Okay, and we're going to finish on this slide here, which is the two test results I did with a couple of the pistons where we've been talking about. 2.8 meters per second, maximum velocity, absolutely flying. A lot of shock dynos out there won't. The one, say, under a 50k would probably be up to a meter per second. Up to 3 meters per second, you're looking at some pretty expensive kit. Mine is different because it's a direct drive. It's not having to push as heavy loads, so I can run it up a lot quicker, a lot faster, and get those type of velocities. But I'm not expecting these vehicles to be getting anywhere near 2.8 meters per second. Again, unless you're doing 200 miles an hour and you hit a very high speed bump. But 40 strokes per second, that thing's going 40 strokes, and on a 39 millimeter stroke. So it is using its whole movement, and it's running right through that. This thing was absolutely cooked after just a few seconds there, and you can see this is 4.3. This is a snapshot of 4.3 seconds through to 4.5 seconds, and you can see the number of strokes, both compression and in rebound, which you can't quite see. But this is just the one compression stroke maximum velocity, and in this particular case, 8 by 1.2 piston had a maximum force of 41.4 kilograms. That's packing. Now, 5 by 1.5 piston, 42.2. And that's probably where I'll sum up the whole spreadsheets and what have you. They don't quite follow what actually happens with these pistons. Why is that the case? Well, and it will sort of allude to where I was going before with a more progressive type of piston style. I would say in sort of simpler way that the 5 by 1.5 is sort of squandering the opportunities that the silicon oil provides it. So the silicon oil provides a resistive force, but because that 1.5, that hole is just that little bit more open, it's letting the oil sort of go through, and it's sort of getting a bit of a free ride. So it's got a lot less damping, but it's not taking advantage of that silicon oil, and in a sense, it's then getting into that transition type flow a lot sooner than, say, a piston with a smaller hole, where it is going to be more of that shear type of resistance, and it can just hold on to that shear type resistance a lot longer. And eventually, because a transition flow is a more inefficient flow, and it's occurring a lot sooner with the 5 by 1.5, it will gradually increase enough to then overtake that 8 by 1.2. Now, if I then took it out even further into some sort of ridiculous speed, I'm sure that the 8 by 1.2 will then exceed the 5 by 1.5 perhaps, but I'm not going beyond 2.8. But that's where the fluids will behave, and that's where you've got to be careful with, say, some of these hole configurations. I hope that made sense. Anyway, thank you again for watching. Any questions, you can shoot me an email or comment on this YouTube, and we'll see you on the next video. Thanks for watching. Bye.